everyone. My name is Woojin Lee from the Electronics and Telecommunications Research Institute in Korea. Today, I'll be presenting our work, SolidCoder, bridging the mental reality gap in LLM code generation through concrete execution. Over the next 10 minutes, I want to convince you of one simple idea. When it comes to verifying code, language models should stop imagining and start executing. Let's start with the problem. Today's leading code generation agents verify their own code mostly through what we call mental simulation. The model internally traces through the code step by step and decides whether it's correct. The trouble is that language models hallucinate. They can imagine an execution trace that has nothing to do with how the code actually learns and then confidently declare the buggy code correct. Look at the example on the right. The model is given a buggy rotate function. It mentally traces it for k equals 1, gets the expected output, and stamps it pass. But the trace itself is hallucinated. The code logic is different from what the model imagined. The bug is real, it just happens to be hidden for that one input. It's like playing chess blindfolded and still claiming checkmate. So, our motivation follows a simple principle: don't imagine, execute. We close this mental reality gap by running the code live rather than picturing how it might behave. Crucially, we found that this gap has two distinct dimensions. The first is the specification gap. During planning, the model overlooks edge cases, empty inputs, boundary values, and so it builds the wrong thing from the start. The second is the verification gap. Even with a reasonable plan, hallucinated execution leads to false passes on buggy code. These two are independent problems, and our vision is to move toward verification you can actually trust, grounded in execution, not imagination. The diagram on the right previews how SolidCoder handles the same rotate problem. It plans for boundary cases, generates property-based tests, runs the code in a sandbox, catches the real failure, and fixes it. This leads to three research questions that structure our work. First, what exactly is the mental reality gap in LLM self-verification, and what are its key dimensions? Second, under a missing Oracle setting, where we don't have the correct answers to check against, how can live execution, rather than imagination, reduce both gaps? And third, how much does our execution-grounded architecture, which we call SOLID, actually improve code generation, and can we separate out its contribution to closing the specification gap versus the verification gap? These three questions map onto our analysis, our method, and our experiment respectively. Here is the core method. The name SOLID captures 5 components. The S is shift-left planning. Before encoding, we proactively ask the model what worst-case inputs could break a knife solution, and we forward those edge cases into the plan. This directly attacks the specification gap. The O is oracle-based assertions. The challenge with execution is the missing oracle. We don't know the correct output for a novel problem. Our key insight is that we don't need exact outputs. We can check properties instead. For example, the output length equals the input length, or the result is a permutation of the input. These are checkable through execution without grounded truth. The L is live execution. Instead of an imagined trace, we run the code in a sandbox. This closes the verification gap. The I is intermediate simulation, a lightweight mental trace light after generation used as a pre-filter. Live execution always provides the final, authoritative verdict. And the D is defensive accumulation. Every failing test we discover is saved and rerun after each fix, so repair never silently reintroduces an old bug. The figure contrasts CodeSim, which imagines, with SolidCoder, which executes. The blue components are our additions. For our experiments, we deliberately chose 3 benchmarks spanning a difficulty gradient. Human Neighbor, with 164 function level problems, represents the easy end. Code Contest, with 165 code forces problems, sits in the medium range. And Apps, with 150 problems, is the hard end. We focus on function level and competitive programming tasks on purpose to cleanly isolate the verification problem we're studying without the compounds of repository navigation. We evaluate 3 models chosen to test generalization across 3 axes: GPT-PO, which is closed source and not OLL trained, GPT-OSS 120B, an open source GPT model that is post-LLVL, and GroPo.1 passed, a non-Chipty closed-source model, are supposed trained with reinforcement learning. Our matrix route is pass 1. A problem counts as solved only if the very first generated solution passes all hidden tests. So, does bridging the mental reality gap actually help? Yes, consistently. SolidCoder matches or beats prior frameworks on every model and every benchmark we tested. But the more interesting story is well, it helps. The biggest gains land squarely on the medium difficulty problems. And that's exactly what you'd expect. Easy problems are nearly solved already, so there's little to gain. Very hard problems are bottlenecked by generation itself. No amount of verification can rescue a fundamentally broken algorithm. It's in the middle ground where mental simulation starts to break down, yet execution can still catch and fix the errors. That's the sweet spot. And crucially, these gains hold up even on the other post-trained models, which tells us the benefit comes from the architecture, not from any single model. To see how the two gaps contribute separately, we removed one component at a time. The picture is clear. The single most important component is shift-left planning. Removing it causes by far the largest drop. This tells us that for complex algorithmic problems, edge case blindness is the dominant failure mode. Live execution contributes less in raw magnitude, but it is irreplaceable. It catches a categorically different kind of error, cases where the model would have hallucinated a correct traceable buggy code. Specification improvements simply cannot reach those. And the two work together synergistically. Better edge case awareness generates richer test scenarios, which live execution then validates with real feedback. Planning without execution still leans on hallucination from checking. Execution without planning only ever tests the happy path. You need both. Let me wrap up with 3 takeaways. First, we identified the mental reality gap and showed it breaks down into 2 independent dimensions, the specification gap, which is edge case blindness, and the verification gap, which is hallucinated execution. Second, guided by one principle, don't imagine, execute, we built SolidCoder. Shift-left planning closes the specification side, and live execution with property-based oracles closes the verification side, replacing imagination with concrete runtime feedback. Third, this delivers state-of-the-art results, and the gains generalize across model families, so the benefit is architectural level. The broader message is simple. As models become stronger generators, the next bottleneck is stronger self-evaluation. Grounding verification in reality, not imagination, is essential for robust code synthesis. And that brings me to the end. Thank you for your attention. Goodbye.